I think that now we're going to hand over to our third speaker today, which is Pete Hardee from Cadence. If you can share your screen, please, Pete.
I'm sharing, and hopefully if I go into the slideshow mode, you see the slide and not the speaker view, right?
Perfect. It's all gone. It's all gone very perfectly. I am going to introduce you and then let you start. So Pete Hardee from Cadence, where he's Group Director of Product Management in the Systems and Verification Group at Cadence. He runs the Jasper formal verification product line and is also responsible for the safety verification solution. The title of his talk is FMEDA-driven functional safety verification for automotive semiconductors.
Thank you, Mike.
Thank you, Pete.
Okay, so we had a great presentation from Hans Leo that started very much at the whole car view, right, including the mechanical systems. Great presentation from Dave on, you know, the approach to really test the from a software point of view, if you like, running on the processes in the system. We're diving a little deeper now and really getting into the hardware, into how we test for the effects of failures in the silicon. And you know, why are we talking about this? Of course, there are a lot of automotive semiconductor companies. Europe is very strong in that area. The growth of automotive semiconductor is pretty strong, and it gets stronger and stronger and stronger the more you're into the sort of new autonomous driving and ADAS sort of solutions there. You see the incredible growth rates for LiDAR systems and that kind of stuff. So, of course, a lot of interest in this. In the States, we see a lot of startups. In the Far East, we see a lot of startups. In the you know, in the European market, it is the players that've been in the business for a long time that we all know and love. What else is going on? Of course, if we look at what was the state of the art in cars 10 years ago, this is an American focus here, if you like, although I guess Jeep is owned by Daimler-Benz. But you know, looking at the Jeep here, basically you've got a lot of distributed ECUs connected by a CAN bus. And we're now moving more towards Ford Mach-E is very much a software-defined vehicle, glass cockpit. We have the you know, basically a zonal architecture that where you have a lot of compute that is connected by a pretty high-performance vehicle network. And of course, the OEMs are interested in that means of communication, not just to differentiate the car based on the software content, but also you know, those you're saving a lot of cabling. So I don't know if you've considered the weight of actual copper cabling in the old style cars, which is being, if you like, replaced by high-speed networking, and that's definitely an advantage of this move to the zonal architecture with high-speed networking. So you've already seen a little bit of the V diagram, and here we have the you know, the ISO 26262 chapters sort of superimposed on that V. One of the important things I want to go into here, which is really spelled out in chapter 9, is the ASIL levels here and the various statistics for the various ASIL levels. Of course, you know, what does this mean in actuality? From what we're seeing, yeah, ASIL A is pretty easy to meet. You've got to follow the processes that are set out in ISO 26262. Fault injection is not required. ASIL B, if you do really good FMEDA, which is failure modes, effects, and diagnostic analysis, very often there is not the need to introduce much in the way of safety mechanisms at ASIL B, and very often you can get away without fault injection based testing. That all depends on the FMEDA. There are, of course, exceptions, and there may be some subset of the system that that you need to introduce a safety mechanism. And the safety mechanisms are often simpler. You can get away with parity. You can get away with error checking and correction. ASIL D, on the other hand, you're talking about some of the mechanisms that Hans Leo was discussing. The dual core lockstep processors that are separated by safety islands and this kind of thing. ASIL C is usually somewhere in the middle, of course. But in order, what this is all about is when I introduce a safety mechanism, I really have to do fault injection to test that safety mechanism is working correctly, picking up the faults that happen, naturally in the system, and the system reacts correctly and fails safe. So that's what we're trying to achieve here. So the cadence flow to achieve that, we start off with the FMEDA at the top there, and I will go into why do you want to use an FMEDA system like Midas as opposed to getting the consultants in that will do all of this that's Excel based. I'll go into the advantages of that somewhat. That is done at an architectural level and a more detailed FMEDA level. We'll go into that a little bit. We have a format which we call USF, Unified Safety Format. It is proposed as something that could meet the Accelera standards. There is a functional safety working group at Accelera. Accelera works as, if you like, an incubation standards group for IEEE. There is also a functional safety working group starting at IEEE. Cadence will support whatever the eventual standard that comes out from IEEE. For now, we have this format which we call USF. I'll go into a little bit how that's used on the next slide. And it does allow us to link up the FMEDA to the safety tools, and there I have, I'll go into a little bit what Verisium Safety does in terms of the fault campaign management. It uses the main verification engines we have at Cadence, which is Jasper for formal, Excellium for logic simulation, also for fault simulation, and now Palladium for fault emulation as well. It links up with the implementation tools, Genus and Innovus, for implementing the safety mechanisms that can be specified in USF. And also there is a mixed signal component, which I won't really have time to go into today, with the Virtuoso and Spectre tools. Spectre is really the tool that does analog fault injection as well for those that need that. So FMEDA, and a little bit the advantage of doing FMEDA if you like, in an EDA tool as opposed to Excel. So at the architectural stage here on the left-hand side, let me just bring up a pointer here so I can show it. So really, what are we doing? We have maybe no design data available, so you're really just working off a block diagram, and maybe you have an idea of the register count and the gate count in the blocks that are being defined. So at that stage, we can get some useful estimations of the failure rates and the distributions, and start defining some of the effects of the failures. Really, what you can do is plug the ASIC library that you intend to use, a little bit about the environmental conditions that you have to meet. And then from there, we have all the calculation engines that can calculate, if you like, the base failure rates, which is what is shown in the screenshot that you can probably barely see here, because it's a little bit small, so apologies for that. Then, we start to see the advantage of using a tool as opposed to, an EDA tool as opposed to, Excel, because the FMEDA solution that we have links up automatically with the design database. So as you're moving from a design estimation to an actual implementation of a design, then the real components and the real gate counts can be read back in, and improving the analysis. In this particular example that we see, I believe we're trying to meet ASIL B here, but when we have all of that realistic design data, we actually get a slightly worse result than the estimation that we started out with at the architectural stage. So we have some, and this is normal. Our single point failure metric is, at this stage is not meeting the standards. So, okay, so what do we have to do? We have to introduce some safety mechanism, and we have to show that that safety mechanism is working. And that's where the verification process comes into it. Fault injection allows you to feedback something called diagnostic coverage. And then you can read in the real, so in this picture on the right-hand side, we've got the optimized safety design that is reading in the diagnostic coverage to check that our safety mechanism is working correctly. And hey presto, we have an improvement in the single point failure metric, and we're meeting our spec. Okay, so that's kind of a little bit the flow that you would go through in FMEDA. It touches every part of the flow. In terms of the safety verification flow, now we have a picture that is it's actually fairly unique to Cadence, that the left-hand side of this, if you like, the good machine simulation, the regular functional verification, looks very, very similar to the right-hand side. We have managed to build our fault simulation environment into the existing tools. So really, it's a very, very natural transition to move from functional verification to safety verification. There's advantages here in terms of ease of debug, in terms of reuse of the functional tests that you have anyway. What's quite common is to take a subset of your functional tests and really capture the vectors from that. So you've got a sort of vector capture and replay flow going on. You have to be very, very careful with that. It's a necessity to do it that way when you have different tools for fault injection than functional verification. But that can be quite error prone. So you need to be very, very careful doing that. Also, the debug visibility is not very good. So actually just reusing the test bench that you have for functional verification, also for safety verification, which is something we can do because it's basically all the same tools. That is a much less error prone flow to be able to do that. We have fault campaign management, and used to be known as vManager Safety. Now Verisium Manager Safety is really the tool that does that. So for anyone familiar with the Cadence flow, you'll already be familiar that vManager will orchestrate and your regressions and sort of manage your tests. It is also where the coverage is collected, and you can see graphical representations of the coverage against all of the entries in the verification plan. And in the case of vManager Safety, you see the diagnostic coverage against each part of the fault list. So where does the fault list come from? The fault list is coming out of the FMEDA analysis that you're doing. You have to start off with a fault list that is specifying where I want to inject faults. You have a strobe list, which is where I want to measure or observe those faults. You have a test list, which is the tests in my test bench that I'm using to stimulate the system in the face of those faults. And then we have campaign configuration, which is the function that Verisium Manager Safety is providing. So that is working with the rest of the tools. It is always desirable to minimize the fault injection that you're doing as much as possible. Fault injection, however efficient your tools are, is an expensive and quite a heavy process. Fault list reduction can happen in a number of ways. Statistical sampling is allowed. especially when your fault list is, of course, large. So your safety assessors will allow some statistical sampling as long as your fault list is large enough. Fault collapsing can be done, and there's structural analysis that can help with that in terms of, effectively, if I have many different representations of what's effectively the same fault, I could have stuck-out faults on many different places which are effectively in the system exactly the same. For example, if I have an output that fans out to multiple inputs, a stuck-at at my one output is exactly the same as a stuck-at at any of those inputs on the fan out. So that's an example of, if you like, fault collapsing and finding out where all of those situations are. There's other things I'll go into in terms of testability analysis that can help you reduce the fault list further. And then there is test dropping, which is basically the phenomenon of in ISO 26262, I only have to hit each fault once. So once I've hit a fault, I can remove that from the list and I don't need to hit it again. That's the phenomenon known as test dropping. And of course, the fault campaign management is measuring the diagnostic coverage, giving you a measure of safeness, back annotating those results to FMEDA, and generating all of the reports that your assessors need. So a little bit more on Excellium safety. There's a couple of ways of injecting these faults, and of course the four usual categories of faults are stuck at 0, stuck at 1, the single event transient and single event upset. So all of these need to be injected. They can be injected one at a time or multiple in terms of concurrent fault simulation. Of course, you get better performance from concurrent fault simulation. You can inject multiple faults at a time, but the debuggability is a little trickier. So a lot of people start off with serial until they've got it all correctly set up, and then use the concurrent fault injection for speed. Actually, for a lot of mixed signal designs that are sort of small d, big A, a lot of folks find that serial fault injection is absolutely enough, but moving on to the big, if you like, digital chips and doing a fault injection for a big fault list, you're going to need the performance of concurrent fault injection. So it's nice to have a solution that does both of those things, and you can move between them at will, more or less. As I said, serial for setup, but you might also want to move back to serial for debug of certain faults that aren't behaving quite as you expect. One thing that we have as well is fault emulation with Palladium, and this brings in a big advantage. I mean, Dave talked a little bit about STLs, right? Software test libraries. So to be able to run a complex automotive chip, and to be able to check that the software stack or the software test library confirms that the system is behaving correctly in the presence of a fault, then fault emulation it has the performance to be able to help you do that. It would be very, very difficult to do that on logic simulation. It's really, the performance isn't there to be able to run software on the, on the processors in the often multiprocessor SoC. So fault injection in emulation is a very good thing to have. Okay, in terms of where Jasper fits into it, I mentioned it a little bit in terms of the structural.
Just to make it aware, Pete, we've got 1 minute left, okay?
Okay, that's great. So we have Jasper, which allows us to do the structural fault list reduction before fault injection. It also helps to do fault propagation analysis, and it's very, very useful to be able to convert unobservable faults to safe faults. And a handful of those can often make the difference to be able to meet your ASIL requirement. So in summary, really, the advantages that we're talking here, it's great to have a true EDA tool for the FMEDA analysis with the links to both implementation for the implementation of the safety mechanisms and to the verification for the back annotation of diagnostic coverage. The links to analog mixed signal simulation and mixed faults simulation is very, very important. The links into the implementation tools and having a good environment for verification management, the coverage, and meeting the traceability requirements that are in ISO 26262. And then, of course, all of those tools need to be certified as fit for purpose. All the Cadence tools meet the TCL1, and the ones that are involved specifically with the safety solution have the TCL2/3 certification, allowing them to be used for any ASIL level. And that is, hope I just finished on time there, Mike.
Perfect.
So
Yeah,
that's what we have in terms of
Yeah.
the Cadence functional safety flow.
Thank you. We have 5 questions, but we'll send them via email if that's okay, and we can answer them directly.
Okay. Perfect.
Thank you very much. Thank you very much, Pete.